Hey everyone, welcome back. So, if you're a focused learner looking for the absolute most direct, high-density path to mastering atomic structure, well, you're in exactly the right place. Today, we're taking a massively comprehensive set of chemistry lecture notes and transforming them into the ultimate visual study guide. We're completely skipping the fluff, we're drilling straight into the core concepts of atomic theory. Think of this explainer as your master PDF guide brought to life, designed to make your learning ridiculously efficient and honestly pretty fascinating. Let's get right into it.
Okay, here's the roadmap for our journey today. We'll kick things off with a quick overview of the historic atomic models, and then zoom way in on Rutherford's groundbreaking gold foil experiment. From there, we'll explore how Bohr's model fixed early flaws, but also where it totally fell short. After that, I'm giving you exactly what you need for your exams, a master frame with all the crucial formulas consolidated into one spot. And finally, we'll wrap up with a rapid-fire knowledge check.
Section 1. The Atomic Models Overview.
To really wrap our heads around modern chemistry, we kind of have to see how our understanding of the atom evolved over time. It was basically a rapid-fire succession of brilliant scientific stepping stones. In 1898, J.J. Thomson proposed the plum pudding model, envisioning this positively charged sphere with electrons scattered throughout it, kind of like raisins in a pudding. But just over a decade later, in 1911, Ernest Rutherford completely upended that with his solar system model. By 1913, Niels Bohr came along and refined the math with his quantum model, which actually held strong until the super-complex quantum mechanical atom model emerged between 1924 and 1927. Today, though, we are focusing heavily on that critical leap from Rutherford to Bohr.
Section 2. Rutherford's gold foil experiment.
Now, this is the experiment that completely shattered early assumptions. And what's really amazing here is the sheer elegance of the physical setup. Rutherford, along with Geiger and Marsden, basically placed a radioactive source inside a lead block. This source fired a highly energetic beam of alpha particles, which, by the way, are essentially just super fast-moving doubly positive helium ions, straight through a tiny slit. Their target? An impossibly thin piece of gold foil measuring just 0.00004 centimeters thick. Surrounding that target was a circular screen coated with zinc sulfide to detect exactly where those invisible alpha particles ended up.
Before we look at the results, it's actually absolutely crucial to understand why they used zinc sulfide for that detector screen in the first place. We have to draw a line between fluorescence and phosphorescence. So fluorescence is immediate, right? The material absorbs light and instantly emits it. But phosphorescence, which is exactly what zinc sulfide does, has a delayed emission. When an alpha particle absolutely smashes into that zinc sulfide screen, it excites the electrons, and they hold on to that energy for just a tiny fraction of a second before releasing it as a visible flash of light. That slight delay and lingering glow, that's what actually allowed human eyes sitting in a pitch-black room to count the individual particle impacts.
Okay, let's dive right into the foil itself. Right at that microscopic layer, literal atomic collisions are taking place. Imagine those heavy, fast, positively charged alpha particles speeding toward the gold atoms. Now, since Thomson's plum pudding model suggested a soft, uniformly spread out positive charge, Rutherford totally expected his heavy alpha bullets to rip straight through the foil with barely even a nudge.
But, science is all about the unexpected. Here are the 3 shocking results that literally changed everything. First up, about 99% of the alpha particles did actually pass straight through, completely undeflected. This proved that an atom is overwhelmingly just empty space. Second, a few particles deflected at slight angles, meaning they were being repelled by a concentrated positive charge. But the third result, this was the absolute jaw-dropper. Roughly 1 in every 20,000 alpha particles hit something so incredibly massive and dense that it bounced completely backward. Rutherford famously said it was like firing a massive naval shell at a piece of tissue paper and having it bounce back and hit you. No way, right? But this definitively proved that 99.97% of an atom's mass is crammed into a tiny, dense, positively charged core, which he named the nucleus.
Section 3. Bohr's Model and Limits. So, Rutherford had discovered the nucleus, which was amazing, but his whole solar system analogy had a massive, physics-breaking plot hole. If electrons orbit the nucleus like planets around the sun, well, they are constantly changing direction. And according to Maxwell's established electromagnetic theory, any charged particle moving in a circular path has to continuously radiate energy. If Rutherford's model were entirely correct, the electron would constantly lose energy, its orbit would shrink, and it would spiral straight into the nucleus in a fraction of a second, a theoretical death spiral. Atoms would just collapse. Niels Bohr stepped in with a pretty bold correction. He proposed absolute stability. He said that electrons stay in specific, fixed, quantized orbits, and as long as an electron stays in its designated orbit, it does not radiate or lose any energy at all.
And this brilliantly illustrates how science progresses through iteration. Bohr fixed the stability issue, sure, but his model wasn't perfect by any stretch. We absolutely must remember its strict limitations. See, Bohr's math only works perfectly for single electron species, like hydrogen, ionized helium, or doubly ionized lithium. The absolute second you introduce multiple electrons, the model completely fails to explain the complex spectral lines. Plus, when atoms are placed in a magnetic field, their spectral lines split into finer lines, a phenomenon called the Zeeman effect. Put them in an electric field, they also split, which is known as the Stark effect. Bohr's model simply couldn't explain either of these phenomena, paving the way for the quantum mechanical model.
Section 4. All formulas in one frame.
All right, we've covered the history and the theory, but physics and chemistry require actual mathematical application. So the crucial point is that you need to be able to calculate the physical properties of these atoms. I want you to literally pause the explainer right now and take a screenshot. As requested, we have consolidated all the critical Bohr model formulas into one single frame for your PDF notes. Notice the velocity equation. The velocity of an electron in the nth orbit equals 2.18 times 10 to the power of 6 multiplied by z over n in meters per second, and right below it, the radius of the nth orbit is 0.529 angstroms multiplied by n squared over z. Keeping this master cheat sheet handy is going to save you massive amounts of time when you're grinding through practice problems.
Section 5, final question and answer.
All right, let's put this focused learning to the test. Here is a pretty complex question pulled directly from the source material. What is the angular momentum of an orbiting electron in the normal state of a hydrogen atom? Think about Bohr's postulate for angular momentum. It's quantized, right? And remember, the normal state implies the ground state, where n equals 1. Now, we aren't going to show you the step-by-step working here. This is a pure recall and calculation test. Got your number figured out?
The definitive answer is 1.05 times 10 to the power of negative 34 joule seconds. If you use the formula L equals n times Planck's constant divided by 2 pi and just plugged in 1 for n, you absolutely nailed it. We've tracked the crazy evolution of the atom, witnessed Rutherford's empty space, and locked down Bohr's math. Definitely keep this PDF guide handy. But I want you to leave with this final thought. If Bohr's beautifully simple equations completely fall apart the exact moment you add just one single extra electron, what kind of unimaginable quantum chaos must be happening inside the atoms making up your own body right now? Keep questioning the invisible, and we will see you in the next explainer.